hyperbolic deflection.
I really appreciate organizer giving me a chance to talk here. Today I give a talk about the real projective deformation of hyperbolic reflection orbifolds. So we consider compact reflection orbifolds of dimension at least 3 by using Klein model for hyperbolic geometry. A hyperbolic structure on orbifolds provides example of real projective structure. If all admits a hyperbolic structure, and such a hyperbolic structure is unique. But we consider induced real projective structure on such an orbifold, then sometimes such an orbifold deform into a family of real projective structure that are not induced from hyperbolic structure. So we will describe large class of compact hyperbolic reflection orbifold with such a deformation. And some part is joined on with Professor Gyeseon and Professor Choi. So first give a definition of a KAIST group. The KAIST group is a group has a group presentation with a set of generator and following relations. So each generator scale is identity and some pair I and j, and we have a Ri, Rj, and Ij's power is identity. Okay. And the polyhedron in the spherical or Euclidean or hyperbolic space is a KAIST polyhedron if its dihedral angles are all integer sum multiple of pi. This polyhedra is important among the other non-obtuse angles polyhedron because group generated by reflection with respect to facet of zeta polyhedron is discrete. In here, facet means codimension one face of polyhedron. So, on the other hand, the fundamental polyhedron of any discrete reflection group is a KAIST polyhedron. So this is a simple example. So this P is a KAIST polyhedron. Okay? And we consider reflection with respect to this line is called R1. Then in this way. And another reflection R2, then we get the and continue. Then we can get the tiling of a two-dimensional Euclidean space. Okay, and obvious, you can think that each reflections are generated. Okay, R1 and R2, R3, and of course reflection is an obvious relation, and two adjacent edges give a reflection R1 composite R2 give a rotation 2 pi over 3. Okay, so this is another relation. So similarly, we can get the following relations. And we have this guy is a discrete group of a group of isometry in a two-dimensional Euclidean space. So we caution by this Euclidean space and caution by gamma, then we can get this object is a coxeter Euclidean coxeter 2 orbifolds. Okay? So we can think that this point on edges is stabilized G2 because this is reflections, and this point is stabilized is a dihedral group D3, something like that. Okay, so this is Euclidean coxeter 2 orbifold, and why is all these things coxeter? Because in 1934, in fact, coxeter classified all the compact coxeter polyhedra in the spherical or Euclidean space. The main idea is that in the spherical space, and Coxeter polyhedra is a simplices. Okay, and in this case, Euclidean space is the product of simplices. So using this fact, the Coxeter classified all this polyhedra. But until now, there is no complete classification of compact hyperbolic Coxeter polyhedra. But we have only some partial result. So to consider the hyperbolic Coxeter polyhedra, we define the Lorentzian space. R and 1 is a n plus 1 dimensional real vector space with Lorentzian product. Okay. So this is example. Okay. So this is a R21. So this disk is a hyperbolic two-dimensional hyperbolic disk. Okay. And this triangle lie on this hyperbolic space, and we can think that each edges give a hyperplane. Okay, each hyperplane give a Lorentzian orthogonal normal vector Vi. So each facet give a one vector. Okay. So in this case, we have a three normal vector respect to Lorentzian in the product. Okay. So using this unit vector, we can get a matrix. Okay. So ground matrix of a hyperbolic polyhedron P is that a system of vectors Vi, and denoted by Gp is simply Gi is a Lorentzian product between Vi and Vj. Okay. So obviously diagonal is 1, okay, because we choose a unique normal vector, and non-opposite entry is of it. It means if the two facets are adjacent, in this case we have some dihedral angle theta, then in this case this value is minus cosine theta. Okay. And for the hyperbolic case, we can get the signature, this ground matrix is signature N1, and also this matrix is obviously symmetry and indecomposable. Indecomposable means that this is does not decompose into a two part of matrix. But the converse is also true. The Bimberg proved that G is an indecomposable symmetry matrix of signature N1 with the following A. Then there exists convex polyhedron P in a hyperbolic space, whose ground matrix is exactly G, and polyhedron P is uniquely determined up to isometry. So we have a hyperbolic polyhedron. This give each facet give a unique normal vector. Using this, we can obtain the matrix. Okay, and this theorem means that somehow we have some one-term correspondence. Polyhedron, ground matrix. Okay. So using this kind of fact, many mathematicians classified some case. The first one is a compact hyperbolic Coxeter n polyhedron with n plus 1 facet, and the simplices. But the dimension, in this case, dimension or less than or equal to 4. Okay, and then continue. And n plus 2 facet also classified, and dimension is less than or equal to 5. And quite recently, Tumakin classified n plus 3 facet Also, we can continue, but still more and more the number of facets increase, and the combinatorial structure is more complicated. So still they get the n plus 3 facet, and also the dimension is less than or equal to a. Okay, but also another important theorem, Bingo proved that there are no compact hyperbolic coxeter polyhedra in the higher dimension. So the dimension is quite big, then there is no compact hyperbolic coxeter polyhedra. Okay? But this bound to not sharp, because still example of compact hyperbolic coxeter polyhedra are known up to dimension A only. So between 9, 10 until 28, 29, we don't know if there exists or not. Okay? So this is an example. So maybe I explained a little more. So each vertex means facet, codimension one base, and if the two faces are adjacent, in this case, if the dihedral angle is pi over n, then we rather n. In this case, dotted line means that two facets does not adjacent. But we more simplified notation is that if the level 2 is just erase edges, erase these edges, 3 is just 1, 4, 2, 3. Going to go back, and in this case, these two facets does not in two facets does not connected by edges, but this means that two facets are adjacent with dihedral angle pi over 2. Okay, right angles. Only these two facets does not adjacent. Okay. So this example is a 8-dimensional polyhedron with 11 facets. So another direction is that according to dimension, like to dimension 2, we already know what kind of coxeter polyhedron it is by Poincaré, and next I explain the Andrew theorem. To explain that, we define the abstract 3 polyhedron C is a cell complex which is topologically 3-ball and equipped with cell structure which can be realized as a convex polyhedron P, and whose I cells corresponding to the I-dimensional face of P. Okay? And the boundary of C is 2 skeleton of C, and the star means dual. Okay? So this example is a 2 skeleton of the cube. Okay? And this is dual. Right? And then another definition is simple closed curve gamma is a K circuit if the I consists of K edges of dual or boundary state. Okay? And for the prismatic K circuit, if in addition all the endpoints of edges of boundary state which are missed are different. So you can see in this guy is a 4 circuit, right? Furthermore, and all the endpoints of edges, this one and that one, another one and this, are different. Okay, so this is a prismatic 4 circuit. Okay. So what is the Andrew theorem? C is abstract 3 polyhedron. For the C is not tetrahedron, and non-obtuse angles are given corresponding to the each edges. then the following conditions are necessarily sufficient for the existence of compact hyperbolic three-polyhedron, okay, which realize C with dihedral angle zij. First one is Fij is the vertex of C, then this vertex, then adjacent edges, incident edges, you have the sum of angle is greater than pi. Okay? And another one is if the three facets form a prismatic three circuit, 1, 2, 3, this make a prismatic three circuit, then the sum is less than pi. Okay? Next one, prismatic four circuit, then this angle sum is less than 2 pi. And finally, triangular prism with a triangular face F1 and F2, then all the angle sum is less than 3 pi. Further, this compact hyperbolic three-polyhedron is unique up to hyperbolic isometry. So I give an example. This is a rebel polyhedron, Lm. So here, top and bottom polygon is M1. Around the M1, we attach the pentagon. Okay, so M1 in this case is 6 gon, and around we attach the pentagon. Similarly, we attach the pentagon. So this kind of polyhedron we call regular polyhedron. Then this guy is L6, and L5 is we already familiar, is dodecahedron. Okay. So for any m is greater than or equal to 5, then there exists unique compact hyperbolic real-world polyhedron, such that all the dihedral angle is right angles. Because you can easily see this real-world polyhedron does not contain prismatic 3 circuit and prismatic 4 circuit. Okay? So we only check the, of course this is not, previous real-world polyhedron is not triangular prism, and there's no prismatic 3 and 4 circuit, so we only check this guy. But this is obviously satisfied. So 3 times pi over 2 is obviously correct. Pi. Okay. So in this way we have a sufficient and necessary condition. What kind of hyperbolic polyhedron exists or not. Okay. So previous time still I talk about the hyperbolic geometry. The hyperbolic structure is a GX structure. Here with the G is the group of isometry of an n-dimensional hyperbolic space, and X is a hyperbolic space. So until now we discuss about hyperbolic structure, and next we move to linear plate structure, which is a GX structure with G is PGL and plus 1R, and X is RPL. Okay. Now, in corresponding unique SL plus minus and SN structure, here SL plus minus is just determinant plus minus 1, and SN is just double cover of RPN. Okay. So now we say, I say, if real primitive structure, then this is just this structure. Okay. So in fact, hyperbolic geometry arises as a thermogeometry of real primitive structure, because previously we think about the hyperbolic disk, two-dimensional disk. This guy is B, right? And so Hn is a open ball B, and isometry, the group of isometry of hyperbolic space is the subgroup of SI plus minus preserving B. Okay. So hyperbolic manifold or the orbifolds naturally have an induced real projective structure. So we fix N, and the V is a real vector space, dimension n plus 1, and G is a SI plus minus. And then we define a projective reflection. Previous hyperbolic reflection, if I have a vector, uninormal vector Vi, then this determines hyperbolic reflection. Okay? But the projective reflection, in this case we need two guides. The reflection R is an element of order 2 of G, which is identity on a hyperplane. So of the form is for the some linear function of alpha and vector B, with alpha B is equal to 2. Okay? So in this case we need two guides, alpha and B. Only satisfy this condition, then this gives a reflection R. So if the elements of kernel of alpha is in fact fixed point of R, because kernel element, if the V is an element of the kernel, then V RV equal to V minus 0, so fixed point. And the reflection at B, put the here, then RB is B minus 2 times B, so minus B. So we call this guy is reflection vector. Okay? And similarly we can define rotation is elements of G, which is identity on the subspace of codimension 2 and conjugate to a matrix, rotation matrix. Okay? And this real number theta is called angle of rotation. So we have a convex and polyhedron in the projective sphere, and previous I said that facet is a face of codimension 1, rigid is a face of codimension 2, and each number is F and E respectively. Okay. So for each facet Fi, and take a linear function alpha I for Fi, and choose a reflection Ri with the satisfying this. Okay. So each facet we have one reflection. Okay. And by making suitable choice of sign, is defined by the following inequalities. Then group gamma generated by all these reflection is a linear constant group if the intersection between the gamma interior of P and interior of P is empty. Okay? For the every non-identity elements. So, and then we call this matrix A is each entry is alpha I bj is a pattern matrix of gamma. Okay. Previously we remember, if you remember the ground matrix, then in fact pattern matrix is a generalization of ground matrix times 2. Okay. Because in this case we choose 2. The the diagonal elements of pattern matrix all the 2. Right? So Bimber proved that the following conditions are necessary and sufficient for gamma to be a linear constant group. So this is obvious. And if for pair I and j, and the non-diagonal element, or the non-positive, and if the one side is element entry is 0, then opposite side also 0. Okay? And if aij and aji is greater than or equal to 4, and or 4 times cosine square pi over nij. Okay? So if the hyperbolic case, the entry is a minus cosine pi over nij, if the two facets are adjacent. So if you multiply, then cosine square pi over nij, just 4 times. So the ground matrix times 2 is give a Cartan matrix, a special case. If the aij, aji is equal to 4 times cosine square pi over nij, then in fact two reflection, ri and rj, composition give a rotation of angle 2 pi over nij. Okay? And of course the group is the dihedral group dnij. So if you think about the reflection group, we have a reflection group, and this gives alpha and b, the reflection vector b. But this alpha I and bi are determined of two following obvious transformation. Okay, so scalar multiple di and inverse. Okay, then we get the same reflection, obviously. So the Cartan matrix A or gamma is defined up to conjugation by a diagonal matrix with positive diagonal entries. So and we define another terminology. So gamma x with a subgroup of gamma generated by reflection in those facets of P which contain x. And PF is a subset of P such that gamma x is finite. And Bimberg proved that gamma is linear coxeter group, then the union of all gamma P is convex. Okay? So this is a P. Okay? And then we apply one reflections, this one, and another one, continue. And this guy, omega gamma, is a convex. Okay? And gamma is discrete subgroup of G, preserving previous interior of omega gamma. Okay? So situation quite, so if this guy P is a hyperbolic case, this omega gamma is exactly ellipse. Okay? So gamma is discrete subgroup G, and the intersection between the interior of omega and P is PF, is homeomorphic to the interior of gamma quotient by gamma. So this guy gives a convex open subset of projective sphere, and this quotient is determined real projective structure on the coxeter orbifold P hat. Okay. In our case, we only deal with compact case. So original omega is equal to interior of omega, and P is Pm because of all the elements of P. That's fine that this gamma x is finite. So only deal with this complex case. So we have a linear Coxeter group, and this gives some omega convex set quotient by discrete group gamma. Then we get the Coxeter orbifold. Okay. So what is the deformation space of real projective structure on a Coxeter orbifold? We fixed Coxeter orbifold, and then but a lot of linear Coxeter group give the same topological Coxeter orbifolds. Okay, so the deformation space of real projective structure on the Coxeter n orbifold is the following way. So we fixed Coxeter orbifold and all the inverse means and obvious conjugation action quotient by this conjugation action, and we call this guy deformation space of real projective structure on the Coxeter orbifold. So previously, if we think about the P is a compact hyperbolic Coxeter and polyhedron, and obviously previous omega is a ellipse, and quotient by gamma is a hyperbolic Coxeter orbifold. Okay, so in fact P has a Coxeter orbifold structure P hat. So question is that what is the topology of this deformation space? Okay. So in the abstract, I mentioned that hyperbolic structure is unique. Okay. But real projective structure is more bigger than hyperbolic structure. So sometimes this hyperbolic Coxeter orbifold still rigid. I mean, still just a one point set, this deformation space. Or sometimes deformation is not one point set. So in that case, we say that projective deformation. So before going to all the deformation space, previously I mentioned that restricted deformation space is the space of P giving a fixed fundamental polyhedron up to projective automorphism. Okay. So original deformation space is just we fix topological Coxeter orbifold. Okay, but in this case, further we fix fundamental polyhedron P up to projective. Okay, so and Coxeter orbifold P hat is orderable if the facet of P can be ordered so that its facet contains at most n rigid, which are ridges of order 2 or ridges in a facet of higher indices. So this is example. So this guy is a triangular prism, right? And then we give order index 1, 2, 3, 4, 5. And then around this facet, we can count the number of ridges which are order 2 or in a phase of higher index. So in this case, this facet, around this facet is has 3 edges, and all the edges in a facet of higher index. Okay, so this is 3. And next one also satisfying this condition, the previous this orderable condition. So in fact, this triangular prism satisfying the these orderable conditions. Okay. Also, obviously, you can check this triangular prism is hyperbolic. How to check? We use Andrew theorem. Just with the triangular prismatic 3 circuit. So there is only one prismatic 3 circuit. This sum is less than pi. In here, the order 3 means that dihedral angle is pi over 3. Okay? This order 2 means pi over 2, something like that. Okay. So 2006, so we proved that the P is a compact hyperbolic Coxeter 3-pole hadron, and P hat is Coxeter orbifolds arising from P. Suppose P hat is orderable, like this example. Then the restricted deformation space is smooth manifolds of dimension 3f minus E minus E2 minus KP. Here E2 is a number of edges of order 2, and KP is the dimension of the group of projective orthomorphism. In this example, in this case, KP is 0. Okay, so what is F? F is 5, and what the number of edges is 9. Okay. And number of edges of order 2 is 1, 2, 3, 4, 5. Okay. So this is 1. So it means that this restricted deformation space is smooth manifold of dimension 1. Means if this is a hyperbolic structure, then there is deformation space dimension 1. So it means that this hyperbolic Coxeter orbifold deform to the real projective structure. So if the point T is hyperbolic, if the point is given by a hyperbolic structure, then we call the point is hyperbolic, and we call a neighborhood of hyperbolic structure the local restricted deformation space. If you use this guy, then just a local deformation space. Okay. So once again, the P hat is projectively deformable respect and relativity to the mirror if the dimension of its local restricted deformation space is positive. If the 0, then we call the projectively rigid relatively to the mirror. If they just consider local deformation space, then we just say P hat is projectively deformable without some restriction. Okay? And we have in fact we consider compact hyperbolic cubes such that each dihedral angle is pi over 2 or pi over 3. Then we use some theoretical part and computation, and we can get the optosymmetry that exists 34 cubes satisfying this condition. For the corresponding hyperbolic, among them, tan is projectively deformable relatively to the mirror, and remaining are rigid relatively mirrors. And further, we consider dodecahedron. Then each dihedral angle we give us some restriction. Then optosymmetry only 13 dodecahedra satisfy this condition. Among them, only one is deformable relatively to the mirror, and remaining is projectively rigid. Okay.
But the answers might have been different if you didn't say restricted deformation.
Pardon?
You could get different answers if you didn't do it relative to the mirrors. Your
Yes, I mean,
We don't know the answers for these cases. It's not relevant to the numbers.
yeah, in this example is we only consider projective relative to the mirrors. Yeah.
Right.
But the total space, total deformation space, we consider next slide.
Okay.
Yeah. Just please wait. Okay, and this computation is available in our website. And next, move to the total deformation space. Okay. So, previous result, to explain the previous result, we define the truncation and polyhedron. If it is an n polyhedron obtained from the n simplex by the repeated truncation of vertices. Okay, so this is a three-dimensional case tetrahedron. Okay, and then one truncation, so we get the triangular prism, and again we continue. Okay, in this way, all this guy is a truncation 3 polyhedron. Okay, in this case, Ludovic Marcuse proved that if the P is compact hyperbolic coxeter truncation 3 polyhedron, in that case, all the deformation space is just open set of dimension E plus minus 3. In here, E plus is the number of ridges or order edges or order greater than equal to 3. So if you consider this example, this is a truncation polyhedron. In fact, this is just we count what is the number of 1, 2, 3, 4. 4 minus 3 is 1. Okay. The total deformation space is just R. Okay, but we can easily see that every truncation polyhedron has, in this case, triangular face. Okay, so obviously cube and dodecahedra is not a truncation polyhedron, but in this case, to explain the local deformation space, we give following definition. First one, delta P is E minus NF plus this guy. And if you remember what is orderable, then this is a weakly orderable. Only slightly definition is changed, but quite different. I mean, the face set of P can be ordered so that each facet contains at most n ridges of order 2 in a facet of higher index. So in the previous is at most n ridges, which is order 2 or in a facet of higher index. In this case, just n or replaced by n. Okay, so we call this is a weakly order. And recent result is that P is a compact hyperbolic coxeter n polyhedron, and P hat is coxeter orbifold arising from P, and if the following two conditions, first one, this delta P is equal to 0, and another one, P hat is weakly orderable, then the neighborhood of the hyperbolic structure in a deformation space is smooth manifold of dimension E plus minus 3. So we only check these two conditions. Okay? Then we know what is the local deformation space of this coxeter orbifold. Okay? So if the E plus is greater than n, then deformable, otherwise rigid. also n is 3 and p is simple polyhedron, then the delta is always equal to 0. So we have to check two conditions, but in this case already one condition is not necessary, so we only check the weakly order. So P is a compact hyperbolic coxeter 3 polyhedron, then also P hat is weakly orderable, then the neighborhood local deformation space is smooth manifold of dimension E plus minus 3. Okay. So another corollary is that P hat is any coxeter orbifold arising from truncation polyhedron is weakly orderable. So means that P is compact hyperbolic coxeter truncation and polyhedron, and local deformation space is E plus dimension E plus minus n. So previous Marcuse result is only concentrated n equal to 3, but he has the shape of all the deformation space. But our case, it doesn't matter dimension, but we only know the neighborhood local deformation. Although one remark is that P is simple and polyhedron with n is greater than or equal to 4, then in fact P is truncation polyhedron if and only the delta P is equal to 0. Okay. So E plus is a number of ridges of order greater than or equal to 3. So, okay. Also, the good news is that every compact hyperbolic coxeter 3 orbifold which has the combinatorial type of a cube, if starting from the hyperbolic coxeter cube, this is everything is weakly ordered. So we know what is the local deformation space of coxeter cube. Hyperbolic case.
If it can be realized as a hyperbolic.
Yes, of course. Hyperbolic cube, yes. Okay. But just a little thing, think about the little thing, then we can easily found the dodecahedron, a hyperbolic dodecahedron, which is not weakly orderable. Okay. But we can say almost all of the compact hyperbolic coxeter 3 orbifold which has the combinatorial type of dodecahedron is weakly orderable. What does it mean almost all? Following sense. If P is a simple 3 polyhedron, P has no prismatic 3 circuit and has at most 1 prismatic 4 circuit, then please remember the river polyhedron does not have 3 circuit, 4 circuit. So let's find this assumption, obviously. Okay. In this case, we just think about the weakly orderable hyperbolic coxeter 3 orbifold over hyperbolic coxeter 3 orbifold. In this case, D is the maximum of edge order of coxeter 3 orbifold. Then this limit, in fact, identically 1. So in this sense, we can say almost all of compact hyperbolic coxeter 3 orbifold coxeter 3 dodecahedron is weakly orderable. But if the condition, we have a condition 1 and 2, okay, and I explained the two conditions are necessary conditions. First condition is this guy is a combinatorial type of the compact hyperbolic four polyhedron, and this is a product of two triangles. In fact, one of the Ilya-Schumann polyhedron. Previous I explained the n-dimensional polytope with n plus 2 facet in this case. One of them. We can give an order, so this polyhedron is a weakly order. Okay. However, we can easily check the delta P is what is E. In here, we can see there is no dotted line. So all the facet is adjacent. So just E is 6 choose 2. Okay, so 15. And N is 4, F is 6, and we can get the 1. So this is not equal to 0. Then in this case, the deformation space is look like this. This point, 1.1, is a hyperbolic structure. And look around this hyperbolic structure, we can see this guy, the deformation space is not a manifold. Also, second condition is that this is an example of three-dimensional polyhedron. If the edge is labeled D, is dihedral angle is pi over D, otherwise all the right angles. Then this guy is not weakly orderable because all the facet around that, the edges of order 2, the number of edges of order 2 is 4. Because this is 4, about this one is that 1, 2, 3, 4. So this polyhedron does not satisfy the weakly orderable condition. But E plus minus 3 is the simply 0 because the number of E plus, the E plus is 3. But this polyhedron have the symmetry along this hyperplane. So we consider along this hyperplane, we think about the in fact bending deformation. So we can get the, in fact, this deformation space is deformable to the R. So E plus minus 3 is 0, but still there is some deformation. So this is a this implies the second condition is also necessary condition. And I give us some sketch of the proof. Is that the main idea is that we have the polynomial given by the Weinbergs, and means that this alpha I and bj, all of these linear functional and vectors are variable, and this guy is satisfying the following equation by Weinberg result. Okay, and then we can check that this number is this one, and so we can make the following map, and then we can define the U is satisfying these following conditions. Okay. In fact, we can get the D hat is an intersection of previous solution space and U. This is exactly linear Cox-Stokes group generated by Ri give P hat. So, and then we consider previous obvious group action on the P hat. Is one is just multiply one side di and another side di inverse, and this guy is multiply G inverse, and G is related to the conjugation by G. So previous deformation space is same as this object. So if we only concentrated the subset, which is the differential of the Wimborg equations, is at the P is surjective, then of course this guy is the intersection part is a smooth manifold. And then we obvious step one is G tilde act freely and properly on the B hat, and we prove this step one, then the orbit space is smooth manifold of dimension in this way. If we compute, then we can get what I want. And so final step is hyperbolic points is lie in the W. Then we solve the problem. And to do that, we just make the Jacobian matrix, and this Jacobian matrix coming from the Wimborg equations. And next, previous this one is if we consider hyperbolic polyhedron, then I mentioned that first one is a normal vector condition, and this is a without Gyeseon, then this is minus cosine pi over nij. So using this hyperbolic equation, this give another polynomial equations. So combine this, we can get the psi. Then using this one, we can make the Jacobian matrix. So we have two Jacobian matrix. One is from the Wimborg equation. Another one is from the hyperbolic equation. So compare two Jacobian matrix and length, and then we can show that by some infinitesimal rigidity, we can show that finally original Jacobian matrix of Wimborg equations has a full length. It means that the differential is surjective.